Welcome back to Codex. Our speaker today is Harm Derksen from Northeastern University. Professor Derksen is an expert in invariant theory. Today he'll tell us about interactions between invariant theory and computational complexity theory. Take it away, Harm.
Okay, thank you, Dustin, for the introduction. So yes, let me take this away. The plan for this talk is basically to talk about relations between invariant theory and complexity theory. Two things I've been interested in, like invariant theory, I've been working on that for a long time. And also kind of questions related to like, how can you compute things, or how efficient can you compute certain things? And also today we'll also explore some really connections to complexity theory, like, what is the complexity of some of these algorithms? Can they be solved in polynomial time or not? And questions like that. All right, so, okay. So the kind of questions I'm going to talk about is kind of the following setup. So in my talk, G is maybe some algebraic group. And for simplicity, I'll just work over the complex numbers. And V is some representation of G. So the group G acts on this vector space V by linear transformations. And then one can consider like some basic questions. So for example, one simple question is, suppose we have some elements V and W in the vector space. Just decide whether they lie in the same orbit. Okay, and as we'll see later in a moment, there are many problems that can be formulated in this way. So I call that the orbit equivalence problem, right? Other questions I'm interested in that are sort of geometric are the question, given an element in this representation, decide whether zero lies in the closure of the orbit. So the closure in this setting can be just a Zariski closure or just a topological closure. And in fact, in this setting, that's the same thing, turns out. A slightly more general problem is the orbit closure containment problem. So given two elements in the vector space, does one lie in the closure of the orbit of the other element? And then the fourth problem, which is of interest, is given two elements, do their orbit closures intersect or not? And all these problems have sort of various applications, and I wonder, like, how efficient can these problems be solved? So just to give an example, let's consider the graph isomorphism problem, okay? So the graph isomorphism problem asks the following. Given two graphs, say on n vertices, determine whether the graphs are isomorphic or not. And this is actually a very basic, interesting problem in complexity theory, actually. So we can actually formulate this in the context of this orbit problem that I introduced on the previous slide as follows. Like to each graph, we can associate an adjacency matrix. And then on the set of n by n matrices, we have an action of the symmetric group, which acts by conjugation. And then two graphs are isomorphic if the corresponding adjacency matrices lie in the same orbit under this action of the symmetric group. So the graph isomorphism relates now to the question whether two matrices lie in the same orbit. So now graph isomorphism is an interesting complexity class, right? So a major problem in theoretical computer science or in complexity theory is the P versus NP problem. So P is the class of problems that can be solved in polynomial time, and NP is sort of the class of algorithm problems for which there's sort of a polynomial size certificate. And graph isomorphism is somewhere in between. But it's actually unknown whether there's a polynomial time algorithm for the graph isomorphism problem. But it's sort of an interesting class because if P is not equal to NP, then this graph isomorphism problem is sort of believed to be somewhere in between. So that just to give some background on this graph isomorphism problem, that's sort of various attempts of proving that there's a polynomial time algorithm. That, for example, this Weisweiler-Lehmann algorithm, or even like a higher dimensional Weisweiler-Lehmann algorithm. It's some algorithm that colors vertices in sort of a way, and also edges, and perhaps even like more complicated sets. And this algorithm, this k-dimensional Weisweiler-Lehmann algorithm, for every k, basically, you have an algorithm. It doesn't always distinguish non-isomorphic graphs, but the algorithm always runs in polynomial time, but it may not actually distinguish all non-isomorphic graphs, but it will work for large classes of graphs. In fact, there are some examples by Sai, Führer, and Immermann that show that there are actually families of graphs that cannot be distinguished by this k-dimensional Weisweiler-Lehmann algorithm for any fixed k. If you can do it for all k, then it will actually distinguish all graphs, but then the algorithm wouldn't be like polynomial time algorithm anymore. Another special case is by Lux. He gave like a polynomial time algorithm for graphs for bounded degrees. So at each vertex, there are only finitely many edges, or there's a bounded number of edges for some fixed bound. And then there is actually an algorithm by Babai that's not polynomial time, but that's sort of what they call quasi-polynomial time. So the running time is like 2 to the power some power of log of n. Although I mean this paper has been on the archive, but it's, so as far as I know, it's not really completely published yet. And it's fairly complicated algorithm. It, among other things, uses this Weisweiler-Lehmann algorithm, but also uses various classifications of regular graphs and things like that. So anyway, here's another problem, which is the module isomorphism problem. So suppose we have like the R is, say, the free, sort of the non-commutative polynomial ring in M variable. So it's called the free associative algebra. And now we can consider n-dimensional modules over R. And given two modules, one can ask, are these modules isomorphic or not? So that's another sort of isomorphism problem. Now, again, we can view this as an orbit problem. So we have representation, which is, so we can consider set of M tuples of n by n matrices. And the group GLN acts on this space by simultaneous conjugation. So it's given by this formula here. So we have this vector space V, which is sort of this set of M tuples of n by n matrices. And then we have the algebraic group G, which acts on it. And now it turns out there's a bijection between G orbits in this vector space and isomorphism classes of n-dimensional R modules, right? So if you have an R module, right, and each of these generators, each of these variables act by a matrix, and so this way you can associate this M tuple of matrices to this module, and basically the module is determined by that. But if you choose a different basis, you get different matrices. So we just have to look at these M tuples of matrices up to base chains. And so basically, that's why we get this bijection between orbits, which of this action that's basically base chains and these isomorphism classes. Now, it turns out this problem is actually perhaps easier than the graph isomorphism problem. Because in fact, there is a deterministic polynomial time algorithm. So with deterministic, I mean it doesn't use any randomization. And so there are actually several papers on that. I only found out recently that there's actually already a paper by Bongertz from 1989 that sort of addresses this question. But there were other authors that probably were not aware of his paper that gave other proofs of this fact. So that's nice. So that there is a polynomial time algorithm. And in some sense, with randomization, it's somewhat easier because in some sense you could, if two modules are isomorphic, you could look at the home space from one module to another. And if they're isomorphic, then basically any random module homomorphism would actually automatically be an isomorphism. But such an algorithm would use randomization, but there's actually an algorithm that doesn't use any randomization. So another question is, for example, so we have this action of GLN on the space of matrices. You can also look at the module degeneration problem. So when is one module a degeneration of another module? And geometrically, that just means that this one module lies in the orbit closure of the other module. And for this, we actually don't have, it's kind of unknown whether it's a polynomial time algorithm. So this is a kind of quite interesting problem, and people working in a theory of representations of algebra would actually be interested in questions about, how can we decide whether one module is a degeneration of another module? And if you work over, instead of the free algebra, you might look at maybe other algebras, which are just quotients of the free algebra. Then one might be able to say more. But then it becomes sort of a more special problem, less general. And then now for the other two problems, so there's also if I scroll back, let's go back to this. So we had this kind of four problems. So the orbit equivalence problem, we can solve in polynomial time for the setup of modules. And the orbit closure containment problem is kind of open, I guess, whether there's a polynomial time algorithm. And for the orbit closure intersection problem, we actually have a polynomial time algorithm. And the null cone membership problem is actually a special case of the orbit closure intersection problem, and also a special case of the orbit closure containment problem. But in any case, we also have a polynomial time algorithm for that. So this was joint work of Vishu Makam, a former student of mine, and myself. And maybe I'll say more about that a little bit later. Actually, I've worked on the graph isomorphism problem. I kind of wrote a paper on this and tried to reduce the graph isomorphism to the module isomorphism problem. Of course, I didn't succeed to find a polynomial time algorithm, but although perhaps I did, but at least I cannot really prove it. But the algorithm that it leads to is actually more powerful than this Weisfeiler-Lehmann algorithms. So it's at least as powerful, but these examples introduced by Seyfur and Immermann that show that the Weisfeiler-Lehmann algorithm does not solve the graph isomorphism problem in polynomial time. These are not really counterexample for the algorithm that I introduced, but I wouldn't be as bold as claiming that my algorithm would be polynomial time. All right. Maybe I'll say something in general about invariant theory. So general setup, again, let's say we have algebraic group G and V is a representation. So in invariant theory, we can consider the following. We kind of look at the polynomial functions on this vector space. So that's just a polynomial ring in n variables. And then the group also acts on this polynomial ring by automorphisms. And then the invariant ring is the set of all polynomial functions that are invariant under this group action. You can think also of this invariant ring as the set of all polynomials that are constant on the orbits, on the G orbits. Okay. Now, if I have some set of polynomials, then say f1 up to fr, then this notation C f1 up to fr, this will be the ring generated by these polynomials. So that's a subring of this polynomial ring. Note that there may actually be algebraic relations between these polynomials. That's allowed. So this subring is basically the set of all polynomial expressions in these f1 up to fr. So here's a sort of a classical example. If we have, for example, the group, the symmetric group acting on Cn by permuting the coordinates, then the so-called elementary symmetric polynomials are invariant. So you sum over all these indices. So basically, you take the sum of all products of k distinct variables, right? And that will be the kth elementary symmetric polynomial. And so the invariant ring in this case is generated by these elementary symmetric polynomials. And in this case, actually, there are no algebraic relations between these generators. More generally, if G is a reductive group, so examples of reductive groups are like, the classical groups like GLN, SLN, orthogonal group, finite groups, product of reductive groups are again reductive. So these are all examples. And Hilbert basically proved that if you have a reductive group, then the invariant ring is finally generated. So there are finally many polynomials or invariants that generate the invariant ring. Hilbert didn't really introduce his notion of reductive, but basically his proof generalizes to this class of algebraic groups. So these are exactly the groups for which the representation theory is really nice. Like every representation is a direct sum of irreducible representations. One example of a group that's not reductive is the additive group. So if we take the, say, the complex numbers with addition, that is actually an algebraic group, but it's not reductive. It's actually true that the invariant ring for representation of the additive group is actually also finally generated by a theorem of Weizenbach. but not if you take more than one copy of the additive group. In fact, Nagata gave a counterexample, which is actually a counterexample to Hilbert's 14th problem. Basically, Hilbert, well, it was a slightly different question, but essentially Hilbert wanted to know if invariant rings are finally generated, and always, and that's not the case. So, for example, in this counterexample, if you take 13 copies of the additive group, then there exists some 32-dimensional representation for which the invariant ring is not finally generated. There are some smaller examples known now, but in any case, that was sort of the first example. But yeah, let's go back to the situation is nicer if you work with reductive groups. So first of all, right, the invariant ring is finally generated if the group is reductive. And then geometrically, we can view it as follows, like these generators, say F1 up to Fr, together they form a map from a polynomial map from V from the representation to R-dimensional affine space. The image of this map would be a Zariski closed subset of CR, so that's some affine algebraic variety. And so then this phi will actually give you kind of a quotient, right? So a map from V to some variety that's surjective, and the map is constant on orbits. Well, for you kind of would like the fibers of this map to be exactly all the orbits, but that cannot really be true in general. But if G is reductive, it still has sort of this nice property that for every V and W in the vector space V, they have the same image under this quotient map, if and only if the orbit closures do not, if the orbit closures intersect. It's kind of clear that if the orbit closures intersect, then since this map phi is constant on orbits, it will be constant on orbit, and by continuity, it will also be constant on orbit closures. So then if the orbit closures intersect, then the constant value on one orbit closure has to be the same as the constant value on the orbit closure. So that means that phi of V has to be equal to phi of W. But the converse is also true, so that's nice. One particular interesting is also this null cone. So you could look at all V such that phi of V is equal to phi of 0. So those are all vectors V for which the orbit closures intersect with the orbit closure of 0, which is just 0. So these are exactly all vectors for which the origin lies in the orbit closure of V. And this is called, this is called Hilbert's null cone. And like Hilbert also studied that, and actually he uses this also in one of his proofs for finite generation of the invariant ring. This was sort of in the second paper that was sort of a more constructive proof of this result. Okay. If we go back to this this module isomorphism problem, so recall that in that case, the group was GLN, and it was acting on the space of M tuples of n by n matrices. So then we can look at the polynomial functions on V, and basically that's a polynomial ring in M, that should be an N here. So I and J are less equal than N. So it's like a polynomial ring in M times N square variables. Now in this situation, we actually, there's a theorem of Procesi and Razmislov that tells us what a set of generators of the invariant ring. So the invariant ring is generated by all invariants of the form. Well, just take some word in the M letters, and then an M tuple of matrices, A1 up to AM. We send it to the trace of this word in these matrices. Okay. And now you can actually easily verify that this is invariant under this simultaneous conjugation action, right? If you conjugate, then all this sigma inverse sigma, they all cancel except at the beginning and the end. And we know that the trace of a matrix is invariant under conjugation. And in fact, you only have to look at such invariants where k is less or equal than n squared. So the invariant ring is generated by invariants of degree at most n squared in this case. Now, I mentioned now earlier, right, this result of Fischer-McCam and I that gave a polynomial time algorithm to decide whether two orbit closures intersect or not. And this algorithm basically uses this theorem of Borchesi and Razmislov and uses kind of this geometric characterization here that this quotient map exactly tells you like which orbit closures intersect or not. So the yeah, so I wrote it down here. So if you have an M tuple of matrices A and B, then the orbit closures intersect if and only if all the invariants have the same value, which means all the traces of words in the A's are equal to traces of words in the B's. So the algorithm is basically as follows. It's pretty simple. You choose matrices Ci, which is just a blocked matrix where the blocks are Ai and Bi. So these are 2n by 2n matrices. And then you look at the algebra generated by all these Ci's. So that's a sub-algebra of the matrix algebra of 2n by 2n matrices. And now you can find a basis of this sub-algebra as a vector space. That's just basically some linear algebra calculations that can be done in polynomial time. So you have some basis, say C1 up to Cm. Sorry. No, I said that wrong. Okay, so we have this matrix C1 up to Cm. We take the algebra generated by those. And then we have a basis of that, and those basis elements are called Z1 up to Zs. But each Zi has this form, is again a block matrix where the blocks are Xi and Yi. And now basically we can test whether the orbit closures intersect. So they intersect if and only if the traces of Xi and trace of Yi are the same for all I. I see
So
there's a
Harm, James has his hand up. James, do you have a question?
Yeah, I think this might be a good place to hear what you mean by the model of computing in C. Are we using floating point? Is this some kind of number field? What's the...
Yeah, that's a good question. So yeah, here I'm just basically assuming that, arithmetic, addition and multiplication in complex numbers just take constant amount of time. Yeah. So
my concern was more precision. If I'm trying to find a basis or generators, the rounding error generally makes it generate the full matrix space. And so you won't find a sub-algebra, you'll find a larger algebra. So I'm just curious what model.
Yeah, so yeah, if you want to sort of, yeah, you would have to yeah, I mean, you could make similar statements, but then you would have to maybe assume that you're working over a number field, or maybe over a fixed number field. or in some way would have to be able to compute efficiently. So if
These invariants would work in a number field is really all that you would need to know. The claims of the invariants would have to just transfer to some number fields. Is that right?
Yeah, so it kind of depends now how the problem is given, right? So I said, like, I just use a computational module such that you can kind of compute with infinite precision, basically, in the complex numbers. But if you don't like that, maybe you can assume that these matrices A, maybe these matrices are all, say, matrices with rational entries. Or maybe all the matrices have entries in some number field.
Okay, thanks.
If you have transcendental expressions, then things might get probably more hairy. Then probably the algorithms, perhaps you could still do it probabilistically, but maybe not deterministically, because then you have the problem like if you do linear algebra, the expressions will swell. And so you cannot really use like the algebraic expressions if you do the linear algebra, but you can just view them as sort of black boxes and then use this like, probabilistic algorithms to test whether things are zero or non-zero. But then anyway, yeah, so I'm kind of sweeping some things under the rug here, like, in terms of computational model, but by the way, I've been talking of the complex numbers. This algorithm actually works also over finite fields, so then you wouldn't have that problem. But I kind of want to stay away from that. But all right. Yeah. One thing I've been actually interested in for a long time is sort of degree bounds for invariants, which is of course also related to like complexity, like how big are the invariants. So usually we introduce these two invariants. The first one is sort of this beta G, which is sort of the bound for the generators, for the degree of the generators of the invariant ring. And then the sigma G is a bound. Okay, so this null cone that I introduced earlier, it turns out, if you look at the definition, it's sort of exactly the zero set. If you take all homogeneous invariants that are not constant, then the zero set is exactly this null cone. And we know that it's a zero set of finely many polynomials. And the degree up to which you have to go to define this null cone by invariance, that I call sigma G. And these two things are actually closely related. So we actually know a lot about this degree bound. In fact, if G is a finite group, then the degree bound for the generators of the invariant ring, you can always take the group order. It's always an upper bound. Again, if you work with the complex numbers. A long time ago, I proved that if G is reductive, then you can bound this beta, you can bound in terms of the sigma. So beta V is less or equal than 3/8 times n times sigma V square. And the sigma V is in some sense polynomial, but I don't want to go too much in detail. But for example, if you have a representation, of an algebraic group, first you have to view this algebraic group as an affine variety, which is given by some polynomial equations in some vector space. And then the representation should be like a rational representation, which means that it's given by polynomial functions in the coordinate ring of this algebraic group. and these polynomials have certain degrees, etc. So there's a lot of data that defines this representation. And one can give sort of a polynomial bound of the sigma in terms of that data. You could also put it in terms of like highest weights of representations and the dimension of V and so on. In any case, so they're basically polynomial bounds for sigma and therefore also for this beta. But this means that as long as the group G is fixed, then you have sort of nice polynomial bounds. But if the group G is not fixed, then you may not have polynomial bounds. So for example, the situation we're kind of interested in where we have this simultaneous conjugation of GLN on M tuples of n by n matrices, there the group GLN actually depends on n. So this result of mine there doesn't really guarantee polynomial degree bounds. Although in this case, we already know that the polynomial degree bounds because of this result of Parchesi. But in other similar examples, we don't really automatically have polynomial degree bounds. Okay, so now I wanted to say, let me just have a sip. Just to say a little bit more about complexity classes. So there's this complexity class P that I mentioned earlier. So these are the decision problems that can be solved in polynomial time. But then we also have probabilistic algorithms. So the class BPP stands for bounded error probabilistic polynomial time algorithms. These are decision problems that can be solved in polynomial time with a probabilistic algorithm. But the answer doesn't have to be always correct, but maybe it should be, you know, the error, it should be, say, correct with probability, say, 90%, okay? So it should be correct 90% of the time. But of course, if it's correct 90% of the time and you just do this probabilistic algorithm twice, then it will be approximately correct 99% of the time, right? So so basically you can get the error probability as small as you want, but for any fixed epsilon, it's going to be you have a polynomial time algorithm. So the class, so the class P is contained in BPP, but it's still open whether these two classes are the same. So there's some problems for which we have like a good probabilistic algorithm for which that's polynomial time, but we don't have an algorithm that's actually polynomial time deterministically. So so the only algorithms that are fast use these probabilistic methods. So one example of such a problem, so basically this is another kind of major problem in complexity theory. So one interesting problem is the so-called Edmonds problem. So basically Edmonds problem asks the following: if you have a subspace of the n by n matrices, can you decide whether the subspace contains an invertible matrix or not? If I reformulate this a little bit, let's say we have m matrices, A1 up to AM, then we can look at the vector space spanned by these matrices. And so a typical element would be like a linear combination of these matrices. And so then I wonder, do there exist complex numbers T1 up to Tm such that this combination is gives an invertible matrices? I can also think of this T1 up to Tm as variables. So these are basically algebraically independent variables. Then this AT, if I take this linear combination, that would be then an n by n matrices, whose entries lie in this field generated by T1 up to Tm, where T1 up to Tm are basically transcendental variables. So this is a transcendental field extension of degree m over the complex numbers. So then it's sort of this matrix is just one matrix with entries in this sort of big field. And so then the kind of equivalent question is whether the determinant of this matrix, which is then some other element in this big field, whether this is zero or not. Now we have a formula for the determinant, but this formula, right, you have the sum of all permutations, right? You take all the products over all permutations with the sign. Of course, that wouldn't be polynomial time because, you know, the n factorial terms. Also, if you use Gaussian elimination, then if you work with entries in this field, then the expressions become big very quickly. So there's not that wouldn't be a polynomial time algorithm if you treat this T1 up to Tm as variables. However, if T1 up to Tm are just constants, then it's just Gaussian elimination of the complex numbers, and then you can do that very efficiently. So that kind of means there is sort of a probabilistic fast algorithm. So if the matrix is invertible for if this AT is invertible, in other words, if there exist variables T1, if there exist constants T1 up to Tm for which this AT is invertible, then basically any random choice of T1 up to Tm will give me invertible matrices with probability 1. Okay. And so out of that, you can basically construct an algorithm that lies in this complexity class BPP. So again, maybe even if these matrices, let's say these matrices have rational entries, then these T1 up to Tm, you can just choose them integers within a certain range. Well, then you can prove that if there exist invertible matrices, then a random choice will be invertible with probability, say 90% or so. Anyway, so the so-called Edmonds problem, this lies in the complexity class BPP, but that it's not known whether there's a polynomial time algorithm that's deterministic, so that doesn't use any randomization. So that's kind of interesting because that might, let's see what's happened here. Now there's a kind of slightly different version. So question is what if the variables T1 up to Tm do not commute? So right here, these T1 up to Tm lies in the field, and of course, these are just commuting variables. But it's kind of interesting. Suppose these T1 up to Tm are kind of variables, but maybe they lie in the free algebra where the variables don't commute, like they lie in the non-commutative polynomial ring. And then we can also look at the quotient field of this free algebra, which is not really clear what that should be. But there is some construction by Cohen, so the so-called free skew field, which kind of plays the role of the quotient field, but for this non-commutative polynomial ring. And so this free skew field is a skew field, and it has sort of nice properties, but the variables don't commute. So now we kind of have also a non-commutative version of this Edmonds problem. So again, we can look at the same combination, linear combination, T1 up to T1A1 up to TM-AM. But now it's a matrix, an n by n matrices where the entries don't lie in this rational function field, but in this free skew field where the variables don't commute. And now the interesting thing is whether AT is invertible actually depends on whether we view it over this function field or whether we view it as entries in this free skew field. So it matters whether the variables commute or not commute. So here's a kind of a example that illustrates this. If you take A1, A2, A3 to be a basis of the skew symmetric matrices, then we know that every 3x3 skew symmetric matrix is never invertible, right? So so if you have a skew symmetric matrix of odd size, it's never invertible. But interestingly enough, if the variables are non-commuting, so then we could still do Gaussian elimination, but now we don't allow the variables to commute. So I can still do Gaussian elimination. So starting with this skew symmetric matrix, I can multiply, for example, the first row with T1 inverse, and then the second row with negative T1 inverse. And then I can use the first two rows to wipe out the third row. But I get, well, these first two entries in the third row, then I get this matrix. Now I get here some expression that is actually non-zero. I mean, it would be zero if the variables commute, but if the variables don't commute, then it's non-zero. And so then you can actually divide this third row by this, and then you can wipe out some more. And basically you can get to the identity matrix after some Gaussian elimination. So basically this free skew field, I won't say too much about it, but basically things, if you have some expression, some formula in this free skew field, it's such an expression is zero kind of means that whenever we replace these variables with matrices of a certain size or of a large enough size, and all the well, some expression is non-zero basically if I can replace the variables by matrices such that the expression becomes non-zero. Okay, so this non-commutative Edmonds problem is not the same as the Edmonds problem, because whether something is invertible is actually different. But now the interesting thing is this non-commutative Edmonds problems has a connection to invariant theory. And the connection is as follows. So basically, let's look at the action of SLN cross SLN on the space of M tuples by N matrices by simultaneous left and right multiplication. So it's very similar to what we had before. Before we had like simultaneous conjugation. Now we have left and right multiplication. And in this case, we also have a description of the generators of the invariant ring. So one such description is by Domokos-Zubkov. I also have a paper with Jerzy Weyman, which give a different set of generators. But for this, actually, this description of Domokos-Zubkov is kind of very useful. And basically, invariance you can get as follows. Suppose we have like an M tuple of matrices, but of a different size, maybe D by D matrices. Then I can define the following matrix. I take the sum of Ti tensor Ai and take the sum of those. So this is like a Kronecker tensor product. So the A's are N by N size, the T's are D by D size, and this Kronecker tensor product will be Dn by Dn. And now I can take the determinant of such a matrix. So I call that F of D. It depends on this M tuple of D by D matrices that I chose. So if you take the determinant, then this will be invariant for this group action of G. It's actually an invariant of degree dn, right? Because you kind of take into the determinant of a dn by dn matrix. And it turns out that the invariant ring is generated by such invariants. In fact, technically, in fact, it's even spanned as a vector space. Good. Now, so it's not clear that we have a polynomial degree bound, right? We don't have like a Prochési's theorem doesn't apply here. And this general degree bound that I had actually also doesn't apply here because again, this G depends on N. The group is not really constant. So this was actually conjectured by Avi Victorson. And Vishu McCalm was a student of mine at the time, and we kind of worked on this. And we were actually able to prove in this case that we actually do have polynomial degree bounds for the ring of invariance and also for the sigma. So in this case, the ring of invariance is generated by these FTs where this T is an M tuple of D by D matrices, where D is at most M times N to the power 4. So the degree of these invariants would then be M times N to the power 5. In any case, it's still polynomial. And what that means is basically that this non-commutative Edmonds problems, we kind of reduce it to the Edmonds problem, because now if you look at these matrices, the sum Ti tensor Ai, if you take this Ti sort of arbitrary, then basically you get a subspace of it becomes sort of a similar problem. The question whether this contains an invertible matrices. Basically, now we have a subspace of dn by dn matrices and asking whether that contains an invertible matrix. So again, we know that this non-commutative Edmonds problems lies in this BPP. But now kind of the interesting thing is that these authors, Garg, Gurwitz, Oliveira, and Victorson, and sort of independently, Ivanjos, Sao, and Subramanian, they actually prove not only does this non-commutative Edmonds problem lie in BPP, but it actually lies in P. And they're kind of two different approaches. So the Garg, Gurwitz, Oliveira, Victorson, that algorithm works with the complex numbers and uses operator scaling and optimization. So it's kind of a numerical algorithm, but it's still kind of, even if you start with, let's say, with matrices that say have entries in the rational numbers, you would use a numerical algorithm, but then you have kind of some kind of stopping criteria. Then if you get sort of close enough to the optimum, you can kind of decide whether so maybe I should step. Maybe let me say one more thing. Like so this question, right? I didn't say this, but this question, this non-commutative Edmonds problem, what it's saying is, what does it mean that this FT, that all the invariants, what does it mean that this M tuple lies in the null cone is exactly equivalent to this non-commutative Edmonds problem, right? Because it says that all these invariants vanish, and that's actually exactly equivalent to this matrix AT being invertible. So basically, just the null cone membership problem is basically exactly this non-commutative Edmonds problem. anyway, so they use operator scaling to test whether something lies in the null cone or not. Now the other authors, their algorithm is sort of more algebraic and works over arbitrary fields. And their work actually uses our degree bound for invariance and for the sigma, the defining equations for the null cone. And the other algorithm also uses bound, but actually they only need weaker bounds actually. And I see my time's up, so maybe this is a good place to stop, I think.
All right, let's thank the speaker by clicking buttons. So I'm going to click the applause button. I'll stop the recording here.